Hi, my name is Amy Gruss. I'm a professor at Kennesaw State University in the Civil and Environmental Engineering Department. And today I'm going to talk about the state of the science for microplastic cycling and removal, and specifically how it relates to modeling. So for this presentation, I'm first going to talk about a little bit of background with microplastics, the emerging technologies that we're seeing, limitations that we currently have, how computational models can come to the rescue, and future research that needs to be done. Microplastics. By now, I'm sure we've all heard of it, but what exactly are they? Technically, they're any type of plastic, so polystyrene, polyester, PVC, as long as it's smaller than 5 millimeters or 5,000 microns in size. And now we also categorize nanoplastics as anything 100 nanometers in size or less. So what causes them? They have two ways of being produced. So we have primary and secondary microplastics. Secondary microplastics are from natural degradation or weathering of larger litter and trash in the environment. And we also have anthropogenic degradation of plastic. So this is just general over and over use from humans and a natural breakdown due to our use. We also have microbeads. So microbeads are a primary plastic, and these are plastics that are already less than 5 millimeters in size, with the specific goal of using them for cleaning or something similar. In 2015 in the US, we banned microbeads. However, we only banned them from rinse-off cosmetics, so you still do see them produced in this country. Some examples that I have here, any foams or fragments or fibers or flakes. Specifically, what they've found in recent years is that the breakdown of polyester clothing in the laundry and the washing machine is a large source of microplastics. So where are they found? Maybe a better question is where are they not found, but we see them in the ocean. That's probably how we first heard about microplastics. We also saw them we do currently see them in drinking water. Not just drinking water out of your tap, but also bottled water. So in a sealed environment, we're finding these microplastics. We also see them in Antarctica and the Arctic Sea. They're currently being found in food, so you might have seen that recent study, how it was found in salt, but we have salt and sugar and even more processed foods like beer, and of course fish is a big one since they accumulate it when they're alive in the sea. And as of January of 2021, scientists in Italy have recently found microplastics in human placenta as well. Pretty small ones too, about 5 microns in size. Okay, so should we care about this though? Technically, the World Health Organization says that there is not enough evidence of these microplastics and ingesting them where they'll be harmful to humans. So the health effects for humans are a little unknown right now. There's just not enough evidence and research out there. However, more studies are pointing to the fact that things can absorb onto the surfaces of microplastics. So persistent organic pollutants like PFAS chemicals, as well as the absorption of heavy metals. And microplastics right now are known to damage aquatic ecosystems. They can alter wildlife's gene expression, growth, reproduction, and survival. Okay, so recent concern has been focused on microplastics in drinking water plants. So the source that we might see them enter the drinking water system is the water body that we're grabbing our drinking water from. So either industry is discharging there and maybe not cleaning it up enough, trash and litter being in our surface water. And then we go through this drinking water process. We have screens in the beginning, which remove large amounts of plastics and debris. Then we go through coagulation and flocculation and sedimentation and filtration and disinfection, and all of that, for the most part, before it reaches us humans, removes about 75 to 98% of microplastics. The majority. That's great, but these microplastics have to go somewhere. So where do they go? They tend to get stuck in the sludge at our drinking water treatment plants. This sludge, for the most part, is dewatered and sent to a landfill. However, it has the potential, when you dewater it, to be using it for beneficial reuse or fertilizer. And all of that water that they're removing from the sludge has to go somewhere, and they tend to send it back to the surface water after it settles for a bit in a pond or something, or they send it back to the beginning of the treatment plant. We also have wastewater treatment that we have to think about. This is another way that they can enter and cycle in the environment. So sources are from our own personal care products that go down the drain, as well as if your city has a combined sewer overflow system, anything that goes down a stormwater drainage system has the potential to be sent to a wastewater treatment plant in a heavy rain event. From here, we also have screens, we have primary clarification, we have biological treatment where we're using those microbes to break down our waste for us. Then we have some more sedimentation and clarification. We filter it, disinfect it, and then we send it on its way to another surface water. So where do the microplastics go? For the most part, we're seeing in the 90s as far as a percent removal of microplastics at wastewater treatment plants, but it has to go somewhere. So again, it goes and is concentrated in the sludge. And while our sludge treatment is a little more involved at wastewater treatment plants, it still does contain microplastics. From there, a lot of times we land apply it, we use it as fertilizer, which it can be cycled into crops and be ingested by humans, or it can stay in your soil and during heavy rain events can also get washed back into the water system. So although in those last few schematics I presented it in kind of a one line and a straight line indicating that there's an endpoint for these microplastics, they actually do cycle through the environment continuously. So for a water treatment plant, we have the sludge that's being separated from the drinking water. That sludge is settled and the supernatant is flows to a surface water, and a lot of times that surface water is the same one they're grabbing their drinking water from. For wastewater, we separate the sludge from the wastewater that gets treated and sent to a surface water. That sludge is now biosolids after it's treated. Those have a large concentration. We might land apply it, be contaminating our food and our soil. We consume that and it might end up back at the wastewater treatment plant as well. So we have to really look at these technologies. So there are thankfully emerging technologies that can remove them from this cycle. One option is reducing the inputs or the sources in the first place, or removing the existing plastic pollution. So if we look at removing it at its source, these are things like laundry filters, stormwater mesh, and booms. At wastewater treatment facilities, there's only one in the world that is actively removing microplastics. Many remove macroplastics, but only one is removing microplastics, and they are actually using jellyfish mucus. It's a company called Go Jelly. It's pretty cool. But a lot of technology out there is used for removing the existing plastic pollution in our waterways. These are things like large booms, mesh screens, skimmers, vacuums, and bubble barriers. So let's take a look at what kind of technologies we have here. So we have the top left photo is a bubble barrier where it just uses air and these bubbles that force the microplastics into a catchment basin. It does that because of the low density of microplastics, so it's pretty easy to move them up and about. We have below that a picture of a vacuum, and what they do is they just vacuum up the sand on the beach. However, on that rig that you see there, they use density separation to separate the sediment from the plastics, and then they're able to just put the sediment and the sand back into the environment. We also have specially designed mesh screens. The ocean cleanup is currently being used to clean up the great garbage patch that's floating around in the ocean. And there is a skimmer that's currently being used called the Marina Trash Skimmer. And while it looks like a dumpster that's submerged in the water, you're exactly right. That's kind of what it is. They have a pump that forces the water in, collects the plastics, the remaining water can go out, and all of those plastics can be captured and disposed of in that black box. Okay, So while it seems like we have a good grasp of all of these technologies out there, there are still limitations. So in order to see if these methods are effective at removing microplastics, it's very difficult to utilize field analysis. Why? There's no standard method for sampling it. There's no standard method for extracting it from your sample, and there's no standard method for characterizing the microplastics that you have. Pretty much everybody is left to figure it out for themselves. There's different methodologies that are produced, but what that means is every single journal article you look at for microplastics is using a different methodology. So there's no way to compare these studies and really get a feel for what's out there, right? And there's also limited studies on these smaller microplastics and nanoplastics as well, so we don't have a good grasp on those yet. So what are our needs? In order to develop our technologies and answer some questions that need to be addressed to optimize cleanup, we have to find hotspots in these rivers, lakes, and oceans. So where our technologies need to be placed. We have to prioritize certain waterways, so locating those specific waterways that we can collect the most microplastics. We need to understand some lake turnover events, since now we're finding that some microplastics do end up being pretty prevalent in the benthic habitats at the bottom of lakes and ponds and the sea. So we have to find out when that lake might turn over in order to see when we might have an increased concentration of microplastics in our outfall. And we just want to look at the effectiveness and feasibility and potentially alter our design to do so. So this is where modeling comes in. There are two approaches. The straightforward approach is to model the movement of microplastics. You can assess horizontal and vertical transport, gradients and temporal distribution, and look at fluxes between the ocean and biota and the different fluxes between the ocean and the coast. What's also very important, though, is modeling the capture of microplastics. So being able to use a discrete phase model for these microplastics and measuring the dynamics of different booms or skimming systems in order to optimize your design. So this figure that I have here on the right is a figure of an instantaneous velocity magnitude flow field. The picture 1 and picture 2 are altering the moorings that are attached to this boom in order to optimize the capture of microplastics. So that's one example of how we can use modeling for our emerging technologies. However, there are still some challenges that we have with modeling, right? So as far as scale, issues with scaling the microplastics, not just the range of microplastic sizes, but that the microplastics can be so small that discrete modeling in a very large area might be computationally prohibitive, right? We also have some difficulties as far as the amount of data that's available to us. So models are difficult to verify since there's still so many unknowns in terms of the microplastic quantity as well as the sizes that we see. Bulk sources of microplastics entering the waterways. Where are they entering? How much is entering? When do they enter? These are a lot of unknowns that we have because our field studies are pretty difficult in terms of analyzing and capturing these microplastics. Okay, but modeling is still a very useful tool. So let's take a look at a use case. So we have an example here of a settling pond in North Georgia. So they grab their water from a lake and they treat it at a water treatment facility. Again, we have a decent amount of removal, but those removed plastics have to go somewhere, and they end up in the sludge. The sludge is separated from the drinking water treatment plant. It is placed in a settling pond, and this figure right here shows our settling pond. After it stays there for a while, the outflow flows into a nearby creek. That creek flows back into a lake, and that lake is where they grab their drinking water from, so it gets sent back to the water treatment facility. So after a long period of time, we're going to see a large concentration of microplastics. But first, we had to take a look at some preliminary data to see what was present. So I already collected preliminary data, and it did show the presence of microplastics in this settling pond. So the y-axis that we have here is an actual count of number of microplastics on average taken from at least 3 samples. I collected the sediment from the settling pond, so the sludge at the bottom, as well as the water on top from the outfall. So the sludge was about 40 grams of wet sludge, and the water sample was 1.5 liters of water. We use the method from NOAA for marine plastic capture. This is not a standard method, though it is agreed upon throughout the industry as a good method for extracting microplastics. So this is from the National Oceanic and Atmospheric Administration. We did alter their procedure a little bit. We altered the density settling time. We increased the length, though it didn't show to increase the accuracy of capturing the microplastics or being able to count them. We also altered the chemical for density separation in the extraction process. The method that they recommended was salt instead of the zinc for density separation, and that also proved to show that it did have a good representation for the microplastics and was able to extract a good amount of the microplastics that we had in our samples. So these numbers that you see here are average count. This is a picture of how we had to count those microbes. You have to count each one by one under a microscope. So thank goodness for my wonderful undergraduate researchers that were able to count all of these plastics for me on our filters. This picture doesn't show a scale, but it's about 100 microns, and you can see from the bright color how you're able to separate microplastics from organic matter. Even in the NOAA procedure, they do oxidize it to try to remove the organic matter. You still do see some sediment and sand present throughout it. Okay, so what are our next steps? Now that we know there are microplastics present, we have a lot of work to do. First, we're going to tackle CFD modeling of the settling pond using a three-dimensional time-dependent hydrodynamic model. We're going to look at the flow, and we're going to look at the capture efficiency of different netting, as well as boom configurations. We're going to take a look at some different circulation patterns and temperature distributions to optimize the location and really determine how we're going to get our microplastics that, for the most part, are on the surface captured in a net or a boom. Currently, right now, we're in the pre-processing phase where we're preparing the lake geometry, but as time goes on and that gets all prepared, we're going to be able to run our model and simulate this settling pond to hopefully implement a technology on site. All right, well, thank you so much for listening to my presentation. I appreciate your time, and if you have any questions, please feel free to contact me. Thanks so much. Have a good day.